Hello everyone. In this video, we will be discussing beam numericals. So, just have a look on the given question. Obtain tip deflection and rotation of the beam shown below using finite element analysis. Young's modulus, that is modulus of elasticity, given as 69 gigapascal and Poisson's ratio is 0.33. So we'll just have a look on the given problem. So a cantilever beam is given of rectangular cross section where left end it is fixed in all degrees of freedom. Right side at the end of the cantilever beam a point load is applied of magnitude 1000 Newton. Length of the beam is given as 0.5 meter, and since the cross section is given as rectangle, the width and height value is given. Width is 0.1 meter and height is 0.06 meter. So before moving to the solving, one must be very clear with the units of all the data. Young's modulus is given in gigapascal, that is 10 power 9 Newton per meter square. Length and even other data is given in meters. So it is better to keep all the data or the given data in the meter unit. So we shall start the problem by writing the given data. So given data, and here I'll be going with one element only, since they have not mentioned any information about the modeling. The whole beam element I'll be considering as a one element. So I have node 1 and node 2. So node 1, we know that we have 2 degrees of freedom at each node. So at node 1 it is V1 and theta 1, and at node 2 V2 and theta 2. Just we'll see that V1 and V2 should be considered whenever a point load is applied or given. So here we can able to see here at node 1 there is no point load is given. So obviously if not given means V1 should be considered 0, and even node 1 it is fixed. So there cannot be any movement. So theta 1 is also equal to 0. So this is how one have to start the problem, that is understanding of the given problem. So at node 1 there is no point load is given, so V1 equal to 0, since it is fixed, so there cannot be any movement. So theta also equal to 0, so V1 theta 1 equal to 0. Moving to this one, at node 2 there is a point load, so V value is there, but what is the point to be noted here is the point load is given in the downward direction. We discussed that in the beginning. Any load which is acting upwards in the beam problem only is considered as positive, but the given load value is acting downwards. So when we are solving the problem, we need to consider the P value as minus 1000 Newton, since it is acting downwards, and theta. So definitely there will be a movement at this particular point, since it is a cantilever beam. If a load is applied on this one, then definitely there will be a bending. So it is so clear that in this problem we will be finding out theta 2 value, will be finding out. We'll just see how to find out that one. So for the practical purposes, a beam must be divided into more than one element to obtain precise enough result. But it is not mandatory. We need to go with minimum of 2 elements. Even you can go with one element also. Maybe if you are looking for very exact solutions, you can go with 2 elements or 3 elements. What is the difficulty or the problem we will be facing when we are going with multiple elements, particularly when we are solving the beam problem is time. So if you are going with 2 elements, 3 elements for a beam problem, something like this, where there is no much complexities in the load, if you are going with 2 element, 3 element means what happens, it consumes more time. You can go with 2 or 3 elements in case if at different points, different loads or different boundary condition is given means, of course it is mandatory to go with 2 or 3 elements. When when the cross section is very clearly given and there is no much boundary conditions, as much as possible go with one element. Maybe in the practical purposes, I'll be going with the two element cases. So see the same thing I have shown here. For the sake of showing the process and the simplicity, let's divide the beam into only one element only. The same thing you can follow, and for the whenever you're solving a beam numerical anything. So before moving to the element stiffness matrix, we'll just with the help of a given data, we'll do this particular conversion. So we say that I is nothing but 1 by 12 BHQ for the rectangle cross sections. So here students should be too good in remembering the moment of inertia formula. If you are facing any difficulty in remembering, means obviously you're helpless, because this is one of the very basic equations. Mostly beams is given, means probably you can expect only three cross sections, that is rectangle and the square. For both we can go with 1 by 12 BHQ, we can go with that. For the circular and even some cases they may ask I cross section, that is very rare case, but you can expect that also. So always remember these cross section, that is rectangular square, both comes under one case, one category, and second one is the very popular one, the I cross section, and even IRT, both are almost same, the second category, and third one is the circular. Usually circular will not be given because there are some chance of the shear force acting on that one, so mostly circle will not be given. So either you can expect rectangular or the square cross section, or else you can go with that I sections or the T sections. So 1 by 12 BHQ for the rectangle cross section, I know what is B and H, which is very clearly given in the given data. I'll be substituting B and H. In case if the square cross section means, of course, both B and H remain same. So 0.1 and 0.06 whole cube. And some students still they may have doubt, sir, which is width and which is height. You can able to see here, width is something always like from one end to another, left to right, either bottom or top. You can able to say left to right. The data means always should be considered as width, and height is nothing but always top to bottom. Any point, left side, right side, top to bottom should be considered as the height, and width is left to right, left point to right point, like both the top and bottom. And coming to the height is always a vertical thing. You can able to remember this thing. So if you are substituting B and H in the moment of inertia formula, we will be getting 1.8 into 10 power minus 6 meter power 4. And we know the formula, the stiffness matrix formula. So EK for the element wise. So since only one element I have considered, directly I will be going with Ke equal to K1, which is nothing but EI by 2A cube. We have the values inside. So 2A is nothing but 0.5 meter, because the length of the given length of the given beam given is 0.5 meter. So since we are looking for A here, so A is nothing but 0.25 meter, and Young's modulus given as 69 gigapascal. In terms of meters, we are getting 69 into 10 power 9 Newton per meter square. So since only one element, so element stiffness matrix even is also called as the global stiffness matrix, which is nothing but E69 into 10 power 9. In the previous slide we calculated it as 1.8 into 10 power minus 6, 2 into A cube. 2A is 0.5 means 1A will be 0.25, so 0.25 cube. Do substitute inside the matrix. So 3 0.75 minus 3 0.75. So substitute in these things and simplify these things. After simplifying, I'll be getting it as 3.974 into 10 power 6 of the same matrix. I'm not doing any change in this thing. After simplifying, we will be getting this thing up. Next step is nothing but we have the next step is the equilibrium equation, which is nothing but K into the V, KV, which is equal to F. So what is K? What is K? This is K. 3.974, the global stiffness matrix. This is into V. So we have two nodes. See here, two nodes. How I will be writing V equation as? For node 1 it is V1 theta 1, for node 2 it is V2 theta 2. And coming to the force, I already said we have force Fs1, Ms1, Fs2, Ms2. The same thing I will be writing in this. So equilibrium equation is supposed to be the K into V into F I will be writing. Next is applying boundary condition. Before solving the problem, we discussed that at node 1 there is no point load applied, so V1 equal to 0. Similarly, it is fixed, so theta 1 equal to 0. So eliminate first row first column, second row second column. The same elimination method process. I will be eliminating this thing, and